So we're going to look at electricity. So, under electricity, today we're going to look at the other part of electricity, which is talking about electric circuit. Just confirm with me, are you able to see what is written on the board? Let's have a smooth flow of discussion. Are we seeing what is on the board?
Yes.
Okay. Good. So, yesterday when I started the topic, I talked about the importance of electricity. For you to use a phone, you need charge it. We use electricity to charge it. For you to use a laptop, to use a microwave, to use a washing machine, we need to have electricity. So it's important that every now and then we get to understand what this electricity is all about. We also get to know the dangers of handling electricity and how best we can prevent ourselves from experiencing electric shock. So the other first component of electricity, like I was saying yesterday, we were talking about static electricity, how we can charge an object, how we can depict the charges that are contained in an object, the instrument that is used for that device, as many as we discussed. Okay, so today I want us to look at this component of electricity, which deals with electric circuit. Now, under the electric circuit, there are few aspects that we need to understand. What they are, how we can measure them, and things like that. Component number one, we have to look at what is current. We need to understand what current is. Number two, we'll have to look at the voltage, or you can call it potential difference, or you can call it electromotive force. Three, we have to look at resistance. Then four, we have to look at power. Five, we have to look at energy. So these are the things that we are going to concentrate on as we go on with our discussion. Under electric circuit, we need to know what current is. We need to know what electromotive force is, the potential difference or the voltage. We need to know what resistance is. We come to power. We also look at the electric energy. So first of all, let us speak on one aspect. Current. What is current? And things like that. So the word current is not very new to you and me. I understand that because when we're looking at thermophysics, we looked at heat transfer, and under heat transfer, we looked at convection, the movement of the process, the method by which heat is transferred from one point to the other through the fluids. And under which we also looked at the way such as the convection current. So that convection current, the word current, what is it that was talked about? So anything to do with current, it's everything to do with the flow. Whenever you hear of the word current, what must be known or what should come to your mind is current. So it's the flow. So let's look at current. When you have a phone, you have a phone here, you have a charger. Or maybe let me give you this. You have a router, you have the power cable, you connect. This goes on the power source, right? So current talks about how the charges will be moving, how electricity will be moving through the wire from one point up to the other. The rate at which these electric charges are moving. Remember, I said the word current is related to the flow. So current, we are talking about the electric charges as they move through the wire. At what speed do they move? At what rate? So the rate of change of the rate of flow of electric charges is what we are calling current. Current, let's say this is the rate of flow of electric charges. The flow of these electric charges through the wire is what is being referred to as current. However, because current is a physical quantity, remember the introductory point of physics, we look at physical quantities, the things that we can measure. So because current is something that we can measure, therefore, that we use to represent our physical quantity, there should also be the units in which this physical quantity is measured. There should also be the symbol for the physical quantity. Like distance, we have the symbol D. Speed, we have the symbol S. Velocity, we have a symbol V, because these are the things that I'm measuring. So current has a symbol. Current has a symbol, capital I. But now you see science, I know it's a bit confusing. One might wonder, in the entire word current, I is not there. But why is it that the symbol, we're using I, which is not even part of the letters that are making up the word current? Remember the rules that we have for elements. Some of the elements have symbols that don't even appear in the entire word. So that is the same case with current. So your duty is go find out what is the origin of this letter I for current. So current, whenever you are told to calculate, the symbol that we use for current is I. So it being the physical quantity, there must be the units in which it is measured. So current is measured in amps. Current is measured in amps, and the symbol for the units is capital A. Not small a. Small a, you're talking about acceleration. So we use capital A, though at times we use capital A for area. I'm sure the letter A to do with electrical components should not be something new at a point. All the 3-pin plug, all the 3-pin plugs, all the sockets that all the plugs that have got 3-pin, we call them 3-pin plugs. they have a fuse. Some of these plugs, the fuse is located right here. Others for an adapter is right inside. But for the most of them, tumankalila up. So it just got a provision for opening it. When you hook it, you remove inside there's a fuse. When you read on that fuse, it's capital A. This A on that fuse represents the current. So as I'm saying, what we are discussing today is nothing new. We'll just be reminding ourselves of certain things that we might have seen, but maybe we don't know what they are. Then, this current, because it is something that we can measure, there must be an instrument that is used to measure it. So current, the instrument used to measure current, the instrument used to measure current is called an ammeter. Just give me a second. Sorry guys, so I went to get an instrument that's used for measuring current. And fortunately, I couldn't find it. I only found the galvanometer. So the ammeter looks exactly like this. The only difference which is there is that the numbers are not aligned like this. The pointer is on the 0. The numbers keep on increasing clockwise. And what we have here is capital A, representing an ammeter. However, the physical appearance of the galvanometer and that of an ammeter, they are the same. The only difference, like I said, the scale. The control, the resetting button, it's the same. Terminals, it's the same. So how you can measure the current, you just get to have a battery, you connect, the positive part of the battery comes here on the positive terminal, the negative part of the battery goes on the negative terminal, and then you switch on rather, the switch. It's going to deflect, pointing at a value which is equivalent to the rate of flow of electric charges in the wire. So, right from what we have seen here, though there is much more that we are going to put up. The other point is this instrument, because we are talking about circuit. So for you to use this ammeter, there must be some form of a circuit. There must be some form of a circuit. We said static electricity doesn't, the charges do not, the electricity does not move. So why do we need a circuit? No. So this current comes under electric circuit because for you to connect the ammeter, there must be some form of a circuit. Then, how is this ammeter therefore connected? Because when we were in 39, we were told that there are two types of circuits. There is a parallel circuit, there is also a series circuit. So here, there must be a particular way in which this ammeter must be connected. So we are saying that the ammeter must or is connected in the series circuit, not in the parallel, and there is a reason for that. So always whenever you find there is some form of a circuit and there's an instrument connected in the circuit, they ask you to determine that instrument which is connected in the circuit. For some reasons, you should go for the ammeter. We're talking about the rate of flow. Why don't we connect in the parallel? So series circuit looks like this. I hope you can see. Series circuit looks like this. You have a battery here. You have some connecting wires. You have a switch. Let me put up an open switch. Then here, that's where you have the instrument. Goes down here, it goes flat connection. So here, that is where we should. Amen. So this can be an open switch. Yes, so this is the battery, the open switch, as well as the ammeter. But the question is, why can't we connect the ammeter in the parallel? Science becomes easy to understand when we connect what we are learning in class, something which is taught in the outside world. So I'll give you an example of a hose pipe. We have a pipe here, very big. The wide lumen is quite big. And then this pipe gets to be subdivided into two equal parts. The amount of water at point A, the amount of water at point B, and the amount of water at point C is different. Now remember, when this water runs through this hose pipe, it reaches this point, it has to be subdivided. We're talking about the rate of flow of charges. These charges that are flowing in a single wire, when they reach a junction, they must be splitted. How much of the charges, how many charges will go here, how many will go here, depends on the appliances that are connected on the two. Therefore, when they reach here, you'll find that even water, I'll give you an example of water. Here, where there's only one pipe, the pressure is there. When the pressure is high, meaning the flow is quite fast. Now, when you reach here, where the space is the same as what was here, but there is a subdivision, the charges are getting splitted. Even their flow will be different. So meaning, if there was a connection somewhere there where we put the ammeter, the rate of flow of charges that we get will not be the exact like the one that is coming from the battery. So that is what we're saying. Now, most times, there's descriptions or the definitions of terms that we have in physics, they point to some formulae. How? Let me show you. Just allow me to move my camera somewhere here. Good. So, we are saying that the current is the flow of charges. Now, whenever I talk about the rate of flow, there must be some time being recorded. There must be some time recorded because this time is the one that will tell us whether the charges took place, the charges took longer. So that is how we can somehow define our current. Now, from here, we're saying that current, which is measured, whose symbol is I, is given by that charge has a symbol. The symbol for charge is Q. And then the symbol for time is T. So this is the first formula that we have made so far in electricity. Current equal to charge over time. Now this Q is a symbol for charge. Now these charges also are measured. We also have their units. So maybe let me put that here. Note that a charge whose symbol is capital Q is measured in coulombs, is measured in coulombs. And the symbol for coulomb is a C. Then number two, it's a very well-known fact, time is measured in seconds. Therefore, other than current, number three, other than current being measured in amps, the other units that you can have for current, because we are saying current is equal to charge, which is measured in coulombs, over time, which is measured in seconds. Therefore, current can also be measured, is also measured in coulombs per second. That's another unit for current, coulomb per second, because the same current is charged over time. So let me put up an example, a quick sample. Because the formula is there, you guys know it. The formula is there, I will not solve it. I'll just put up the question here and then leave it open-ended for you guys to discuss. So we are saying that question 1 reads as follows. A motor uses current of 20 amps. A motor uses a current of 20 amps for 10 seconds. So this motor here uses 10 amps of current, or it's rated 10 A. Just stand on for 10 seconds. The question is, how much charge flows through it? How much charge flows through it? That's a question for you. First, you have 30 seconds to solve it. Quick sample says the motor uses a current of 20 amps. It's rated 20A. It's just turned on for 10 seconds. How many charges have already thrown through the motor? Fast, 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 fast. You solve it. When you solve it, you type there the answer or you put up the hand, I'll be able to attend to it. 30 seconds. The motor uses 20. Okay, so someone is ready for the answer. Says 200 coulombs of charge. Another one says 200 coulombs of charge. Okay. More answers should be coming. Only two answers. Please bring them out. Another one says 200 coulombs of charge. Thank you so much. Now let's do it together. We will not disturb our formula. The formula remains intact. Just maybe do a little bit of the disturbance down here. So we are saying that current is the rate of flow of charge. Small t. So current is equal to charge. We don't know the charge is what we're looking for, rather. And then how much of current do we have? We have 20. Here at the point of substitution, even if you don't include the units, you are good to go. Over the time there we are told it's 10. It's a simple grade 9 cross multiplication kind of mathematics. So 20 times 10, we definitely have 200 C. So it means already 200 coulombs of charge will pass through that motor within 10 seconds. Now look at the bulbs in our homes, those security bulbs that we leave on throughout the night. How many coulombs of charge flow through them? It's at this point where you find that if you have a spotlight located by the tank there, it's on. The entire week, some of these lights don't even switch them on, off, rather. You'll find that there's a lot of consumption because some of these appliances that we have are rated differently. Some bulbs are rated 18 watts, others are rated 200 watts, spotlights, most of them, the bright ones, 200 watts, 150. There are even those that are rated 500, 400 watts. So those ones, how many coulombs of charge pass through them the entire night? That's why we report a lot of electrical consumption in our homes. So that's what I'm saying. The topic that we're doing today is nothing new. We're just trying to remind ourselves of certain things, certain symbols that we see in our electrical appliances written somewhere there. Maybe we just don't know what they are. Okay, so do we have questions before we go to another physical quantity? Can we move on?
Yes.
So definitely your answer was all right. It's 200 coulombs of charge definitely flew through the 20 amps rated ammeter just for 10 seconds. The second one is one abbreviated as ELMF. ELMF, I call it LMF. LMF stands for electromotive force. One word, electromotive, then force. That's our EMF. Now, when you say electromotive force, what is it? And whenever you Here the word force in physics, we say it's either a push or a pull on an object. So these charges as they move, okay? These charges as they move, they carry energy. Forms of energy we learned them at grade 9. There's potential energy, there's kinetic, mechanical, gravitational potential, chemical, and many other forms of energy now. These electric charges, as they flow through the wire, they carry energy. And it is that energy, when one person is electrocuted, that energy is given to individual cells in the body. That's why you hear anayuma and things like that, because the charges that this energy, the energy that these charges carry is a lot. So the EMF we're talking about, now look here, let me have a circuit. There's this charge 1, there's charge 2, there's charge 3. And we have a huge battery. Guys, stop here a second. Sorry, yeah, so I was saying that this is the battery. I'm just giving an example. The battery. From this battery, that's where the energy is coming from. The battery, this is of electrical energy, remember? And these charges, all of them are coming to pass through the battery as they go. When this charge passes through the battery, part of electrical energy will be given to the charge. Another one passes there, will be given to the. Let me give you an example of a party. When you go for a party, there are people serving, and then we line up in a queue with our plates. You reach this point, you show them the plate, they add macaron. We go to the other one, they add chicken. We go to the other one, whatever they are adding. So this is what happens to the charge. When they are passing through the battery, each charge is carrying a little bit of energy. Now remember, the energy that we are carrying, just like for a party, the amount of food you are given, some of us, we don't relent. This is my food until I finish. Others will say, quite well, this food is quite a lot, I'm not going to finish. Part of it, take it home. So the amount of energy given to each charge, part of it is used, part of it may remain. So just on that point, that's where we have a clear-cut distinct between potential difference and electromotive force. Electromotive force is you being served food, the amount of food each one of us is getting as we line up for the food. So we are saying that electromotive force, EMF, is the amount of energy supplied to each coulomb of charge. The amount of energy supplied to each coulomb of charge. So that's what we're saying. So we have energy and the charges. So let's say we are given a lump sum of energy, which was given to some huge amount of charges, then we can know how much each charge was getting. So we are saying EMF is equal to the amount of energy supplied a coulomb of charge. So the amount of energy supplied to each coulomb of charge, that's what we are calling EMF. EMF, electromotive force. You might have heard of low voltage. At that point, when in our home we're experiencing low voltage, the amount of energy each charge. Yes, so I'm sorry about the network here around here is not that good. At the party, some of us have got manners that are not very good. I'm not going to call them bad manners, but manners that are not good. The amount of food you are saved doesn't mean you're God saved. Don't finish that food you are saved at the party. Part of it, just pack it. There's no harm. Pack it nicely, bring it to me. I'll put it nicely for you. Now, you also have to take note that this energy we are talking about is measured in joules. The coulombs, energy measured in charge, and the EMF is measured in volts. So, the EMF, the first unit that I'm going to give you is joule per coulomb or volts. Whose symbol is V. At times in physics, they do ask us to do derivation of formulae or maybe providing alternative units and things like that. That's why I'm giving them all. EMF, which is measured in volts, the first unit that I've given you is joule per coulomb because energy is measured in joules and the charge is measured in coulomb. That's why I'm saying joule per coulomb. The other one are the volts. So when you open the back part of the battery, you look at the voltage capacity. If it says 4 volts, 7 volts, what does it mean? That's what we're discussing today. Then potential difference, rather, not potential difference. Potential energy. Potential difference. Now, this is you. At a party, you are given food. The food that you are given here, Mbale Azura, the very big heap right on top of it. Are you going to eat that food? Or are you leaving it? So this coulomb of charge is passing, given quite a number of energy, quite a huge amount of energy, which we are calling the EMF. Now, this energy it is carrying as it goes through the wire. Remember, in the wire, there are a lot of appliances that we've connected. There's TV, the stove, there's microwave, there's a fan, there's an AC, there's a bulb. All those are connected in the circuit. So this bulb, how much of the energy that it has will it share with an electric appliance so that that electric appliance can convert that form of energy it is given to other forms? Fundamental of conservation of energy, we can't create it, we can't destroy it, but we can only convert it from one form to the other, and this is where we are. So this energy it is carrying, as it passes through the wire, there is a bulb. The bulb receives part of the energy. The bulb converts that energy into a useful form, which is light. We also have the wasted energy, which is a minimum of sound and a little bit of heat. So all that energy which has been converted to other forms after being supplied with this charge, that's what you are calling the potential energy or potential difference rather. So potential difference is the amount of energy converted to other forms by each coulomb of charge, by each coulomb Now, because we're talking about the amount of energy supplied, the energy is already here. Charge is already here. So EMF has the same units as the potential difference, which are what? Which are volts. Which are volts. Which are volts. So now this potential difference, the electromotive force, how we measure it, how much of energy is supplied to other form, to each coulomb of charge, how much of energy is converted to the other forms. The instrument that we use to measure is called the voltmeter. So right here, that's where I end. I'll just talk about the voltmeter, how it's connected, how it's used. Then we end here because this is already 11:30, which we're supposed to go for break. So I'm not going to wrap that part. Just allow me to drag my camera on the other side. Good. Bingo. So we are saying the instrument you did measure voltage is called voltmeter. Its symbol is V. Then you are saying the voltmeter is connected in the parallel circuit. Always. We connect the voltmeter always in the parallel circuit. So the illustration is we may have the battery here. This is our battery. And then we have, we want to measure how much of energy is being converted to heat and light by this bulb. So this is our bulb. I'm going to write it inside. This is our bulb. So I want to measure this bulb here, how much of electrical energy when the charges are passing through here is being converted to the other forms. Forms, that's light and heat. So we are saying parallel, so meaning the ammeter, the voltmeter should be connected parallel to this item here. Therefore, we are going to have a bit of a branched kind of connection, and this is where we put voltmeter. So the voltmeter also has a symbol V, like I indicated on the ammeter. This is a galvanometer. The ammeter and the voltmeter, they are almost the same. But except that for the ammeter, they indicate whether it's DC for current, they indicate whether it's DC or AC. Actually, it must be DC because DC has a particular way in which the current moves. But for AC, it changes the direction. We are likely to have something like a galvanometer here so that it shows the direction. It shows that current is going in either direction. But here we are saying we use DC because DC is either, if it's going in this direction, it has to be that direction. If it's going in that direction, it has to be that. So even the current that we measure with the ammeter, the ones that we use in the labs, it must be indicated that it's DC. But at that advanced level, it can be used DC. So the voltmeter looks exactly like this. The only difference is that here we have a V. This one's supposed to have a G for galvanometer, but the voltmeter we have a symbol capital G. So thank you so much, guys, for your time. At this moment, I leave it open-ended for your questions. Much more of the work will be sent for you guys to do. Questions? Questions? Do we have questions?
Mr. Mnenga, can you please move your camera to the next board?
To the left side. You want to write what's there?
Yes.
Don't worry, I'll capture it, then I'll send it to you.
All right.
Let me just move right away. Bingo. So here is the question for you guys. Now, if you have not, this presentation that we've just had will be uploaded on YouTube. The link will be shared, but you guys, you are busy watching my videos, you don't want to subscribe. Subscribe. And in fact, the homework, I'm not going to give you now. Let me tell you this. The other day I made a video. I posted it to quite a number of you. There was only one viewer. Now, I'm not saying you view my videos. It's entirely up to you. But the content which is there, that's what I want you to see. So if you don't want, don't view my video, but write the content. So the work, I'm not going to give you here. I'm not going to send it on WhatsApp. The description of the video, that's where I'm going to put it. So don't watch my video, but write my work. These members are very clever. Can we say we are good to go for break now? Can we say that we are okay?
Yes.
Thank you so much, guys, for joining. The next set of questions, the next lesson will be at 11 hours. Thank you so much.